So this week we're talking about entanglement. So you probably would have heard of entanglement in quantum mechanics, kind of a pretty famous concept. And it's one of the things that makes quantum mechanics definitely different to classical physics. So, of course, you can say there's no superposition in classical physics and so forth, but to some extent you can, say, mimic some of these things in classical physics too. For example, if you've got two ocean waves, then you can have a superposition of just regular waves, right? Just water waves. So it's not that things like superposition doesn't exist in classical physics. In fact, they do. But what we've learned is that the context is a bit sort of different, and so you can have things in two places at once, which you wouldn't think is possible, but it is possible. But entanglement, on the other hand, is something that just does not exist in classical physics. It's something that I think these days people now think is really one of the most central elements that makes quantum physics kind of special. So it's kind of an important topic. So let's get started, if this will work. Here we go. Okay, so just following on from what we learned in composite systems, just to recap on that, if you have like two-part composite system, then we learned in the last set that composite system could be written, most general state can be written something like that, where the wave function here is something with some two labels here because there's two systems, and the wave function is sort of coefficients over every possible combination of states, right? So if there's two qubits, then there's like 4 combinations. And what we learnt there was that there's a special type of states, which are called independent states, where, as the name suggests, this is a special case of a composite system wave function where you can write it as a kind of a product like this. So the special case where there's sort of a tensor product here, which I've abbreviated, between these two states, but Alice has some particular state and Bob separately has some state, and you could write this in the composite kind of picture, but this basically means that the coefficient here has to take some special form, so it can't be the most general thing like that I wrote up here. It's to be kind of this product form where it's like A vector, B vector, and then multiplied instead of this more general thing. So what we can kind of see from here is that we can actually distinguish two types of classes of states, right? So the state of the set of all states, if we consider it to be this kind of circle, so it's a Venn diagram, then some subset of it is some independent states, and more generally, the state is if it's not an independent state, then what we say is that these are so-called entangled states. So actually, the definition in terms of pure states is pretty simple. We're only dealing with pure states in this course. So in this case, basically anything that's not that form is entangled. So it's entangled states. Definition is simple enough. Okay, so so why call it entangled? What's this word entangled? Well, okay, so from the definition, I guess you can see already that, okay, if you define it as anything that's not that, then somehow, so if it's an independent state, then you can write it as a product, and they're kind of, what we saw is that they're kind of, well, they're independent of each other. So it's like a independent distribution, so they're unrelated to each other essentially. But as soon as they're entangled, they're kind of, there's going to be some correlations between the two systems. And so this kind of property that there's some correlation between them is, well, part of the reason why it's called entangled, but it's actually a bit more than that, as we'll kind of see. Okay, so let's look at just a simple example, just to get the feel of it. So this is the most general 2-qubit state, so there's 4 coefficients there. This is the most general independent state, so the coefficients take a special form here. And an example of an entangled state is this one. And you can see that it's entangled just by, well, what you can do is you can say, okay, well, suppose it's of this form, and then let's now try and find the coefficients here, right? So, okay, so suppose it's independent. We're going to do it by sort of proof by contradiction, if you like. So suppose it's this one. Okay, so there's no 0, 1 or 1, 0 here, right? So that basically means that we demand that it's, A0B1. A0B1 has to be 0. Also, A1B0 has to be also 0. Okay, then, okay, so I've got these two equations to satisfy. Now, I need to make them 0, I need to make one of these variables 0, right? So from this equation, I can suppose, let's try A0 is 0. But then A0 doesn't appear here, so I need another condition. Okay, so now I need to set another variable to 0. I can't really do A1, because if I set A1 to 0 and A0 to 0, then it's not in the normalized state, right? So I'm forced to do B0 0. Okay, and then this A0 0 implies that A1 is going to be 1 for normalization, then B1 is 1. But then this is not that state, because using these parameters, I'm going to get the state which is like 1 1, because if you choose this parameters, then, you know, this times this is 0, this times this is 0, this times this is 0, and the only one that's non-zero in this form here is 1 1. But that's not the right state. I was trying to write that state. So so basically, it's not possible to write it in this form, this state, and so it's an entangled state. Okay, so that's an entangled state. Actually, there are, in fact, there's many different entangled states. In fact, if you just pull some random numbers here, it's probably going to be entangled, because actually there's sort of, this blue region is actually much bigger than the yellow region. Yeah. So, there's some four special types of states, 4 special entangled states named after this guy, John Bell. And these are so-called maximally entangled states, because we're not really going to get into it so much in this course, but you can actually also quantify, like give an actual numerical value to how much entanglement a particular state has. And it so happens that these ones have the most amount of entanglement. So by those types of measures, an independent state like this would have 0 entanglement, and this one has sort of the maximum amount of entanglement. So often people will talk about these Bell states because they're the special kind of, they're the sort of extreme examples of entangled states. So you can have also partially entangled states, if you have some different coefficients. So these are actually all orthogonal to each other. So just to show you that they're orthogonal, so let's just take, for example, like the first, so if we've got this state, 0, 0, 1, 1, so I've got that state, and to show that it's orthogonal, what do we do?
Times it back into show 0.
Right, yeah. So just multiply it by the conjugate version. So suppose we do the second one there, right? Okay, so take the inner product between, say, the second one and the first one. And so this 0, 0 and this 0, 0 is, well, okay, sorry, I put these factors of so this is a factor of a half overall. 0, 0 overlap with 0, 0 is 1, and 0, 0 overlap with 1, 1 is 0. 1, 1 overlap with 0, 0 is 0. 1, 1 overlap with 1, 1 is 1, but then there's a minus sign here. And so this is 0. So these are orthogonal to each other. You can check that the other ones are orthogonal, but it's kind of easy to see that the third one and the fourth one are orthogonal to the first one because, for example, if this one was 0, 1, 1, 0, same state. Now 0, 0 and 1, 1, that doesn't even appear here, right? So there's no states actually in common, so it's kind of immediately 0.
Professor?
Yep.
So how do we quantify the degree of entanglement?
Yeah, I was going to talk about that, but then I decided not to talk about it.
So why does it say the maximal
entanglement? Yeah. Okay, so this sort of goes slightly beyond the course, but there's a way of writing any state. So let's okay. So I'll give you a little bit of an idea of how this works. Okay. 1, 0. 1, okay. Here's our general state. Okay, so because the entangled state is basically, it's of this, sorry, an unentangled state or an independent state is of this form. So let's just try and factorize it, okay? So, because if we can factorize it, then it will be definitely not entangled. So let's try and factorize it. So we can do that to some extent. So we're going to factorize this from the first two terms, factorize the first qubit. Then from the second term, factorize the second qubit also. Okay. And so what? Okay. See. I was going to show you showing that it's entangled, well, the degree of entanglement, but I just realized that it's a little bit more complicated than I thought.
So is it like drawing a picture of two different circles that have overlaps, and then we have another two circles that also overlaps with kind of the previous picture? But
Yeah. Yeah. Okay. Well, yeah. So one way is, yeah, that is kind of what you're getting at is one approach that some people take to quantify entanglement. So what you can do is you can first you do something like you work out some way of working out what the distance between two states is, right? So say you have some kind of distance measure between two states like this. So and there's many definitions like this, but there's this kind of relies on working out particular properties of a particular formula that show the distance between two states satisfies some axioms of distance. So things like there's various quantities like relative entropy and things like this. And then what you do is you say, okay, here's my space of all states. Now you've got some distance metric, and you know what all the independent states are. And so say here's your state here, and then you can define entanglement as basically some minimization. And let's say of all these independent states, say 5. So you minimize basically your particular state over all these independent states. And essentially what that's doing is sort of finding kind of this distance here. So you can define entanglement in this form. So that's a kind of quite a general way of defining entanglement. But unfortunately, the formula is not very easy, because essentially what you have to do, imagine you had to do this on a computer, you would basically run through all the possible states that exist, right? And then you've got to, run through all the possible independent states that exist, and then find which one is the closest one. So it's a highly numerically intensive kind of task. So there's actually a much better formula for quantifying the entanglement, which is, and this was sort of what I was trying to describe, but I realized it's a little bit more complicated, and I'm not sure if I can really explain it to you without going into a huge amount of detail. But there's a formula that looks like this. So it's like minus trace log of rho, and rho is the partial trace of this matrix. So if this is over system 2, then it looks like this. So this is a partial trace, and this is the state that you have here, and then you calculate this quantity, and then
okay.
it's the entanglement.
I should have.
I'm sure it means nothing to you. So what I was trying to explain here, and then I realized it's actually a little bit more complicated than I thought, is that actually there's a way of writing any state in this so-called Schmidt form, And well, okay, so let's write the general formula now. So there's a way of basically rotating the bases on both Alice and Bob's side, such that you can write it in this way so that it's basically as diagonal as you can sort of get it. I mean, in the sense that you have basically orthogonal vectors, and this one could be in two different bases. Okay, so and then you have these coefficients. And so for an independent state, these coefficients are like 1, 0, 0, like this. So basically this is just a product state, right? But then for an entangled state, this will be, might look something like, 0.8, 0.1, 0.1, so forth, something like this. And what you do is you say that, okay, well, basically independent states have this distribution, entangled states have to involve several terms in this sum, and then you, the reason why the formula looks like this is because this actually, I don't know, have you guys done entropy somewhere?
Entropy.
Yeah.
Is that some concept in
It's like statistical mechanics, but it comes up in a lot of places actually. Yeah.
Is that H or S?
Yes, it's H or S, yeah. And what this formula actually is doing is actually looking at this distribution and saying, okay, well, if the distribution is like quite flat, like this, so we can look at actually, this lambda, if it's very flat, like things with large entropy have a large probability distribution. You can actually regard this thing squared as a probability distribution. And if it's very flat, then it has a large entropy. If it's very spiked, then it has a low entropy. And so basically this one eventually results in the entropy being 0, or in this case the entanglement, and entangled states have a large entropy. And so what this is basically doing is just measuring how flat this distribution is, and converting that to a number essentially. Okay, so I don't know. This is why I didn't want to get into it. This is why I decided that I was not going to talk about it in the course. Okay, but anyway, maybe that will give you a little bit of an idea. Okay, so you may have to just believe me and say that these states are the states that have the largest amount of entanglement, and there exists various formulas for quantifying how much entanglement, putting a numerical value to it, and that's the sense that it's maximally entangled. Okay, so, but I think maybe what's maybe a bit more interesting in a way is just to understand why these quantum states have different kind of correlation to classical states. Okay, so let's just look at this entangled state 0, 0, 1, 1, and just to get a mental picture in your mind, suppose Alice and Bob are in possession of these two particles. So these are the particles that they have. And they're in this entangled state, okay? And they're at the opposite ends of the Earth. Okay. And they both have measurement devices that they can measure their respective particles. So we've done, a fair bit on measurement, so I think you know basically how this works. But when you do a measurement, because these are independent devices, it's equivalent to, you can say that Alice does the measurement first, and then Bob does his measurement, and then they look at their combined results, and then they can work out the composite system measurement. Okay, so we have this state. Okay, Alice does a measurement, so she'll get either 0 or 1. Okay, because there's a 0 or 1, and she'll get that with 50-50 probability. And then Bob will do his measurement. Now, we should think about what actually happens to the state in this sequence. So, okay, so we're starting with 0, 0, 1, 1. Often I'm just going to drop the normalization because, okay, fine, I won't. Okay, so probability 50%. Alice, this is Alice's measurement, right? And when Alice measures this one, we can do it in terms of the whole projection operator stuff if you like. So for example, Alice does that. She measures the state, here's our initial state. And so this is like 0, 0, sorry, oops. 0 projector, multiply it by the state. Okay. And then so this one, when it projects onto Alice, only this term is going to survive because the overlap of 0 and this 1 here, the first one, which is Alice's qubit, is 0, right? So 0 with 0 is going to give 0. Sorry, this is not TensorFlow. So Alice's 1 will be in 0, and Bob's 1 will be in 0. Yep.
Is the first 0 is Alice state and the second 0 is Bob's state?
Yes. Okay. So let's write it out fully without my usual shortcuts. But what this means is that. So the entangled state is actually this one, and this is Alice's measurement. So both of these are Alice's qubits. So this one is going to act on that qubit there. So we get 0 overlap with 0, but we've got this one, so this one here becomes this one here. Right? And then this one here, nothing really happened to it, so it just sort of carries through. This one also acts on here, but then 0 overlap with 1 is just 0, so this one just vanishes. So there's a sort of a plus 0 there. And the probability of this happening is a half, and you can see that because you can just square this coefficient. Okay, so after Alice's measurement, basically what happens to the state it's in 0, 0. Okay. And for the other outcome, it's in 1, 1, because you can see if you change this to a 1 projection for Alice, then it will act on this one only, it will kill this one, and you'll just get this state. Okay. So now, now Bob's going to do measurement. So if the state now is this thing, what is the probability of Bob getting 0?
1.
Yeah, 1. So this, with probability 1, 12 will get 0. And with probability 0, you get 1, the other state. So basically this doesn't happen. Right. And similarly, the probability of getting 0 on this branch is 0. And the probability of getting 1 for Bob is that one. So, I mean, we sort of broke it down in this, but I mean, we could have easily just looked at this state and said, well, okay, so the coefficient of this one, that's Alice getting 0, Bob getting 0 is a half. Alice getting 1, Bob getting 1 is half. Right? Okay, so half, half, and 0, 0. Okay. I just sort of broke it down just to be very explicit. So,
Professor, can we just inverse the process?
Yep.
Let's say that we first measured in Bob's measurement.
Yeah.
So we'll get a different
Yeah.
result.
No. You'll always get the same result.
Okay.
Yeah. You always get the same result because actually these measurement operators of Alice and Bob, so the measurement operator of this one, MB, because this is Bob's qubit, these operations actually commute because they're acting on physically different systems. So because these measurement operators commute, the ordering does not matter. So you always get the same result.
And is there a possibility that, let's say that Bob has a half and half probability, and then A has a 0, 1 split of probability?
Yeah, I think so. Yeah, so that would be a different state. So maybe if we started in this state, this would also be an entangled state, and in this case, it would be similar to here, except that this would be 0 plus at this point. And then Bob, when he measures in the 0, 1 basis of this plus state, then he'll get 50-50. So there is such a state, but well, we're looking at this particular state. Okay. I mean, it's if you have that situation, then it's actually not so clear that there are correlations, because then you'll get a half, and then a half. So basically, every outcome will be a quarter, and then it's not so clear that there's correlations. But in this state that we have, it's clear that there's some correlations here. So you might sort of go, oh, okay, wow, quantum mechanics got correlations and stuff. Is this, it's entanglement. It's amazing. Actually, this is not amazing yet, because you can completely have something similar with just regular probabilities, because probability theory, also has correlations. So there's, we don't have to have this exotic quantum theory to have correlations. So, for example, you could have exactly the same kind of result in this classical setup. Say you've got these two guns here, and they're randomly sending particles, but then half of them are blue and half of them are red. But then the guns are always set up so that they send the same color. Yeah. So this is a situation where you basically get the same result. When Alice gets a red ball, Bob also gets a red ball. Alice gets a blue ball. Bob will always get a blue ball because we set it up that way. Okay. So just having correlations is not anything amazing. We can do that all the time, probably. So what's the amazing aspect of this? Well, the amazing aspect is not just that they're correlated, but you can also get the correlations in other bases. Okay, and so remember that our quantum mechanical particle or measurement device, we've got like settings on it, right? We've got the plus minus basis setting, or any basis settings. So we could equally do a measurement in a different basis, in the plus minus basis, and actually it's still correlated. So this is sort of the magic of these Bell states, and show this. So here's our state, 0, 0 plus 1, 1. Now let's do our usual basis transformation, where we write the zeros in the plus, minus, and then the ones as plus state, minus state. And if you make those substitutions, you can see that actually these cross terms, for example, look at this plus and then the minus on the first one, that's got a plus sign here, right? But plus minus here will have a minus sign, so they actually cancel. And then the minus plus states also cancel. So in the end you have this state, plus plus, minus minus. So this is exactly the same quantum state. So it's not like we've done a basis rotation or something like that. It's literally the same state. You know, it's precisely the same state. We've just rewritten it in a different basis.
Brad, I think you left something in the second line because there's like a square root of 2.
Oh yeah. Yeah. Okay. So the.
You mean, well, how should we square root of 2, 1 over square root of 2?
Yeah, I think on the second line, yeah, it should be 2 root 2 on the bottom. Yeah. Because yeah, that's right. Yeah. Because we've substituted here, and then there's a root 2 for each of these ones. So it's 2 root 2. Yeah. But the final line is correct. Okay, so now let's see what happens when Alice and Bob, now they put both of their measurement devices in the plus minus basis scene, and then they make a measurement. Okay, so you know, this state looks exactly the same as the previous thing, except that everything's plus minus. So actually, the whole thing is basically the same calculation. So you basically still get these correlations. So when Alice measures plus, then Bob will get plus. And when Alice measures minus, Bob will get minus. Okay, so now is it amazing, or is it still the same story? So I would claim that this is actually amazing, because if you think about what happens, suppose we think of the experiment like this, right? So we've got Alice and Bob, they're separate ends of the Earth, okay? And then say Alice just kind of randomly chooses between the 0, 1 basis or the plus minus basis. Okay? So she kind of totally unpredictably, she just changes to either one. So what that means is that if Alice chooses, say, this basis, then Bob will get either a 0 or 1. Yeah? So basically this scenario, so Bob gets 0 and 1. But if Alice does plus minus basis, then Bob will get actually plus or minus. So actually what Alice is doing is actually changing the nature of the state that Bob gets. And in fact, this actually happens instantaneously. Like, it's not like there's some signal, you know, across the universe that is transmitting this information. It's actually happening instantaneously, and it's faster than the speed of light. So the reason why I made this experiment across the ends of the Earth is so that, you know, they're quite far away, so that you can tell that, you know, it's kind of instantaneous if you have a precise enough measurement. So this is actually what's really weird about quantum mechanics. Not so much that you can have correlations. Always have correlations. That's normal stuff. It's that actually this basis, it's the fact that these states are correlated in any basis, and that's a special property of the entangled states. But this state is actually entangled, it's correlated, but it's correlated in any basis that you choose. Plus, minus, 0, 1. Actually, you can actually choose any basis and it still has this property. And if you do a measurement, then it actually apparently sends that information instantaneously. And this is what Einstein famously said is really something that's bizarre about quantum mechanics, that there's this kind of spooky action at a distance, because apparently Alice is influencing what Bob will get, without any forces or, any kind of information, or, there's no waves traveling from Alice to Bob, or there's no light signal, or there's nothing. It's just some kind of non-local effect that Alice can influence what Bob will get actually purely from this quantum kind of effect. And in fact, this is what Einstein was saying, that there must be something wrong with quantum mechanics, because how can you possibly have this? It doesn't make sense physically. Now, you might be wondering, okay, but so Einstein said that nothing can travel faster than the speed of light, right? I don't know if you're familiar with this kind of concept. So Einstein, theory of relativity says nothing can travel faster than the speed of light. There's a cosmic speed limit. That's kind of a unbreakable law of physics. Yet quantum mechanics seems to actually break this law. So which is right? Is it is quantum mechanics right, or is Einstein right that nothing can travel faster than the speed of light? Now, very strangely, it kind of can still coexist, and the reason and the way that people justify this is to say that, okay, well, it's true that Alice can influence Bob's state and get 0 and 1. But the key point is that, and this is how you get around the sort of Einstein's, it's faster than the speed of light kind of thing, is that the key point is that, yes, but it's completely random. So it's 0 and 1, so the states are definitely, different from this other case, but it's random. And then because it's random, there's actually no way that you can use that information to, for example, make a device to communicate faster than the speed of light. So for example, if you measured any variable like x, y, or z, you always get 0 because it's totally random. And so even though the states that they're getting each time they do the experiment are definitely different, in this case, when Alice does this choice, Bob will definitely get either plus or minus. Alice does this choice, Bob will definitely get 0 and 1. These are definitely different states, but you can't tell because it's random. So this randomness kind of totally spoils everything in a way, because if it wasn't random, then we could communicate with aliens. So
their claim is that it essentially passes on nothing to.
Yeah, that's right. Yeah. So it's a kind of a funny loophole. Like, Einstein said you can't travel faster than the speed of light, yet this one looks like you can, but then if you try and do anything with it, you end up you can't, because it's random. It's like you're this close to having some superluminal communication device, but you just can't get there because it's random. If it was even just like not quite random, it was slightly less random, then you could just get a little bit of a signal. But because it's random, the signal gets totally wiped out. Yeah, I also think this is a really weird aspect of quantum mechanics that is probably, I don't know. I mean, people say they understand it, but this is really quite a weird aspect. Questions?
So if you say that it's all random, so why should we learn that? Because we still use quantum computers these days. So is it the same as in this lecture? I mean, can we control those random things to make it meaningful to us?
Yeah, so there's no way to control the randomness, because that's sort of, yeah, nobody has been able to, I think, control the randomness. It's fundamentally random, at least. That's how people understand it. So if you could control the randomness, then you could, again, communicate with aliens. But you can't control the randomness. And so, yeah. So yeah, very strange. Okay. So there's a way of actually mathematically showing, like actually quantify this kind of effect that quantum mechanics has sort of more correlations than it's possible with classical physics. There's a way to quantify this. And the reason why this is important is, if you remember a couple of lectures ago, we had all those different interpretations of quantum mechanics, right? So we, the one that basically everybody uses is this so-called Copenhagen interpretation, where you say that things, state kind of randomly collapses, and before you make the measurement, sort of is in this particular indeterminate state. And remember, there was the first one, which was the one which I attributed to Einstein, is to sort of remember there was that one where with the plane crash, the realist interpretation, where you view the wave function as being it's got this probabilistic aspect because we just don't know something about the system. So remember, there was that example that I gave with the plane crash, where we know that the plane has crashed somewhere within 400 kilometers of a particular point, but we don't know where it is. That must be not because it's spread evenly over the 400 kilometers, it's because we just don't know where it is, right? And so it's a way of interpreting probability as due to lack of knowledge, right? So actually this Bell's so-called Bell's inequality can actually rule out that interpretation. So it can show, based on quantifiable particular inequalities, that you can actually show that quantum mechanics, it just cannot be consistent with that realist interpretation. And people really made a big deal of this Bell's inequality. You know, people have said that it's perhaps the most profound discovery in science. That's quite a claim. So whether you agree with it's the biggest discovery of science, but definitely I think a lot of people think that it's quite a profound kind of thing. Okay, so this one actually we can easily show using the techniques that we've had. So I'll show you how this works. So basically the setup that we're going to look at is something like this. So again, we're going to start with some entangled state. Alice and Bob are going to do some measurements. And there's one restriction that we're going to make, which is that our measurement box only has two settings on it. Okay, so we can only choose two settings on it. Generally we can do all kinds of measurement-based settings, but this box is a particular brand, and we bought the cheap version. It's only got two settings. Okay, and then each time you do the readout, it only gives two outcomes too. So it will only give either 1 or -1. So this is our outcome, right? So this is our, when we do the measurement, it's either 1 or -1. I use 0 or 1 here, but 1 or -1 is more conventional in this context. So we can also consider kind of a classical version of this exact same setup. So imagine we've got some source here sending out blue or red, maybe balls or something. It's a box with like just two settings, and the readout is always like, okay, I wrote 1 or 0 in this case. So basically this is what Bell did. So Bell said, okay, well let's look at this classical version of this setup. Now, what is the most amount of correlation that I could possibly observe with this particular setup that I have? Boxes with two settings and outcomes, which are two variables. What is the most amount of correlations? And the way that you can kind of describe this is that, okay, well, I've written it as red or blue balls, but maybe it's a little bit more complicated than just red or blue. Maybe there's all different colors. Maybe there's actually a huge amount of information that's being sent by the source. It's not just like some two binary kind of amount of information, but it's as much as information as you want actually. So the underlying particles might have whatever, millions of gigabytes of information that is being transmitted here. So let's call all that information that you're sending, or by that I mean, if I was just sending red or blue, that would be like some binary digit that I'm sending. If I'm sending more information, then it would be some variable with a larger number of degrees of freedom. And so maybe some variable lambda goes between, say, 0 and 3 billion. Okay. And so because this is some kind of random thing, there's going to be a probability distribution over that random variable that I'm going to be sending. So there's some lambda, that's the thing that goes between 0 and 3 billion, and then we've got these probability distributions as a function of that, all the different degrees of freedom. And because we're looking at correlations, trying to figure out what our correlations are going to be in terms of this probability distribution. So, basically, from this kind of setup, Alice and Bob want to reproduce the same kind of thing as we saw in the quantum case. Okay? So, in the classical setup, we can define things like averages of various observables. a bit like how we've been doing. Well, in fact, exactly like how we've been doing. So we've got some probability distribution over these variables, and we've got some observable. These are the values that you average over, right? And because there's two settings, there's two different functions for Alice. So when we put it in setting 1, it's got this function A, and when we put it in setting 2, then it's got A dash. Because it's the same particles that are arriving, but you can process it in some different way according to what your switch setting is. And we've got the same thing for both. Okay? And these values have to be only -1 or 1, because our output values are always either -1 or 1. Okay, and I'm not going to show you the proof, but what you can show is that in such a situation, if you measure these correlators, which are like products of these A's and B's, so there's 4 types of correlators, because there's 2 settings each for Alice and Bob. So if you combine these correlations, then you can show that actually any classical variable always satisfies this inequality. And the way that this formula works is that one of these things has a minus sign somewhere. So it doesn't actually matter which one, because we can redefine our variables in some way, such as to put the minus sign on any one of them. But there's always one with a minus sign somewhere. So that's the classical case, right? And what you can show is that actually in the quantum case, you can actually get something which is larger than this 2. So in the quantum case, you can actually show that it can get the same quantity can be as large as 2 root 2. So there's this famous number 2 root 2 in the context of Bell inequality. So what this shows is that actually quantum particles do have actually something more than classical particles. They really have more correlations, and you can really quantify it. It's not just my, funny example that I was showing with the bases and sort of a hand-waving argument like that. This is something you can really go and measure, put a number to it, and then say that, well, definitely this has a different behavior to classical probability theory. You just cannot describe quantum mechanics with some kind of probabilistic theory. So it actually rules out this interpretation of quantum mechanics, the one that Einstein, kind of favored, but actually disproved Einstein on this point. Einstein was right about almost everything else. On this point, he was kind of not, well, to this point, people think that Einstein is kind of wrong on this point. But, geniuses somehow often would have some way of always being right. Like, famous example is Newton. Newton was always thinking, light is a particle. He was saying when he was alive, that light is a particle, building all these theories about light being a particle. And then they did an interference experiment, Young's double slit experiment, and basically they said, oh, Newton's wrong. And then 100 years later, people go, oh, light is a particle after all. It can be both a particle and a wave. So it's like, okay, he wasn't wrong after all, actually. So, anyway, so at this point, we believe Einstein is wrong at this point. Let's actually just do a quick calculation on this, because it's probably easier to see how this works when you actually do something. So let's look at this kind of classical setup first, okay? So let's I said that each of these particles have maybe a huge number of degrees of freedom, but it's just to keep that story simple, let's say that it's just 2 variables, red and blue. So half, so half of these particles are red, half are blue. And these boxes, the settings, you can have any rule for the A's and the A dashes that you want, okay? But I've kind of arbitrarily chosen some rule like this. Each of the A's and the A dashes and the B's, they have to have -1 or 1. But I can choose these values here as I sort of wish. So I could of course have this one as -1, this one as 1. In fact, I could have had one where both of them are 1 and both of them are -1. That's also okay too. So so long that each of the outputs are 1 or -1, and I have a consistent rule for each A or A dash, I can choose this whatever way I like. But let's just do it for this case that I did here. So so AB, can you see what that will evaluate to? So let's just do each term by term. So this term here, average value of A times B.
Can you just give us an example?
Okay. So yeah. Okay, so A, B, so my rule here is 1 minus 1, 1 minus 1. Okay. So this is the outcome. This is red, this is blue. So A times B is, well, just the multiple of these two. So it's 1 and 1. Yeah. And the probability of this happening is a half and a half. So the average value of A and B, because it's 1 both cases, is of course a half times 1 plus half times 1. So that's 1.
Average value of A, B. So
well, maybe I said outcome, but say bold. Because remember what happens is that, so we've got 2 boxes and some source here is Alice, Bob, and it's sending out some ball and it's like red, right? So when Alice gets a red ball, the rule that we have here is that gives a value of 1. Right? And when Bob gets a red ball, the rule is that it gets a value of 1. And then what they do is, well, maybe first they collect all their data. So they go red, red, blue, blue, red, blue, blah, blah, blah. And then they've got their values for each one. And then to take the average, we're just doing classical probability here, right? Take the average, then they multiply those 2 values together, and then they just find the average value of whatever this AB thing is. And because in this case, either case is 1, the average value of AB is 1. No? No?
So we'll just verify the theorem.
Yeah.
Okay.
So, okay, so for, I think you can just sort of do it in your head without writing anything down. So, A times B prime, so we're looking at these two columns here. What will this be?
-1.
Yeah, -1, yeah. And A prime, and then B, this one.
Same as AB.
Yeah, so that would be +1, right? Yeah. And then A prime, B prime, what about this one?
+1.
+1, no, I think it's -1 because A prime, B prime, so each case, it's like one, when you multiply these two, it's -1, right? When you multiply these two, it's -1, right? So it's basically always -1, no matter if it's red or blue. So if it's -1, no matter if it's red or blue, then its average value is always going to be -1. So another way to say this is that according to these rules, this observer will say A prime, B prime. This is anti-correlated because it gives the opposite value each time. If A prime for this one, it's the same, right? Gives the same value each time, so they're correlated. This pair is anti-correlated because it's giving the opposite results every time. And just to give a slightly different example, so let's choose a different rule here. So say B is just 1 no matter what the outcome is, and A is 1 or -1. So in this case, AB will be 1 or -1 here. And then in this case, this will be minus, and this will be 0. So this is a case where there's no correlation actually, and you can see that because for the red case, it gives the same value. For the blue case, it gives the opposite value, so it's kind of not correlated. You only get correlations if they consistently give the same value, or they consistently give the opposite values, then it's anti-correlated. But if they don't, there's no real relation between the two, then it just gives 0. Okay, but I didn't do that example. This one, okay, and then what you do is just substitute this one into here. Okay, so this was 1, this is -1, this one was 1 + 1, sorry. This one gives 1, because this has a minus sign, this is +1. This is +1 too, but this one is -1. So it'll be 3 - 1, which is 2. And you can kind of play around with this, but there's basically no way of getting something bigger than 2. If you choose anything like this, then you can see that these things are going to give 0, right? And if you want to get a value, so the statement is that this is always going to be less than 2. So if you're trying to get something bigger than this, it's basically not really a good idea to choose something like this, because if some of your correlators are 0, then okay, you're not going to make a very big number, right? So ideally, what you want is actually to somehow choose something here so that all these 4 values are like 1 + 1, right? So ideally, what you want is that to be 1, this one to be -1 to cancel out this one, this to be 1, and then this one to be 1, right? So we were close there, but not close enough, because this one was -1. And it's basically, you can play around with this and try and figure out if there is some way of doing it. What you should find is that there's basically no way of doing it. There's no way of choosing these functions so that it's bigger than 2. So that's the classical case. So that's the statement of the so-called CHSH inequality, named after after 4 guys. Klauser, Horn, Shimoni, some other guy. So let's look at the quantum case, but I think we're sort of running out of time. Yeah, maybe I don't want to rush it too much, so let's leave it there. But what we're going to find is that if we do the same thing in the quantum case, we can actually beat that CHSH bound, and we can get a number which is larger than 2. And that quantitatively shows that quantum mechanics is different to classical physics. Okay, well, we'll show that.